Hello everyone, today I'll be presenting Lab 5, Falling Slinky. To begin with, the purpose of the lab is to model the motion of a stretchy slinky dropped from static equilibrium using computational models and experimental data. Here is a preview of this lab. So we use two tools, Tracker to obtain experimental motion data and glow strip to simulate the ideal motion computationally. Ultimately, our goal is to understand why the bottom of a slinky stays nearly stationary at the beginning of the fall and compare the real and predicted motion. In this lab, we apply Newton's second law, which states that the system changing momentum is determined by the net external force. So F net equals to delta P over delta T equals to M multiply A. Also, there are two key forces on the spring, the gravity and the internal tension. We also need to consider air drag during the fall. And when these forces balanced, the net force is zero, and the acceleration is zero. It explains why the initial stationary bottom of the slinky. According to the diagram, there are two forces on the spring. So for the system, it's the spring itself, and the surrounding include the Earth providing gravitational pull. So this is what I got from the tracker analysis. First, the bottom of the slinky remains stationary until the top of slinky falls to the bottom position. While we'll focus on the bottom change later, we can first see the top movement. So this graph shows that the vertical position as a function of time observed in tracker reflects its falling motion in the vertical direction for the top of the spring. Okay, let's go through the coding part. So we first set the initial condition. The mass of the spring is 0.218 kg, and the calibration height we use is the human height, 1.75 meters. Here is the initial position we get from the tracker analysis, and the velocity is 0 in all directions. So in the first while loop of our computational model, we simulate the stage with the bottom of the slinky stationary. During this period, the net force of the bottom is the 0, and the gravity is pulling downward, but the tension from the stretched upper course exactly balances. In this loop, we update velocity, position, and time step by step by Newton's second law, but the bottom remains fixed because the acceleration is 0. In the second while loop, the slinky begins to fall, and at this point, the tension is no longer enough to cancel gravitational force at the bottom. So we now include the drag force, which acts opposite to the direction of the motion. The code again updates the velocity, position, and time based on Newton's second law. So this is the result part. This final graph compared the experimental motion from tracker and the predicted motion from glow script simulation. So they both show the bottom remains stationary at first and then starts falling. However, the tracker data contains small fluctuations, while the computational model is smoother, and there are several possible errors here. There are three main sources of error. First, environmental factors like air disturbance can slightly disturb the motion. Second, human error in clicking tracker point frame by frame can introduce offsets in the measured position. So why does the bottom of the slinky remain stationary? When the slinky is held at the top, the tension within the slinky balances the gravitational force acting on the bottom part. This means the net force on the bottom is 0, so it remains stationary initially. Only when the top falls far enough that the tension can no longer balance gravity does the bottom start to move. Also, what if we put a large weight at the bottom? Should it remain stationary? It depends on whether the slinky can provide enough tension to balance the increased gravitational force from the weight. If the slinky is long enough or has a large enough spring constant to generate tension equal to the weight's gravity, the bottom weight can stay stationary until the top of the slinky falls to the point where the tension can no longer balance the weight's gravity.